Okay, let's go over some of the homework problems from. Let's do all of them. Homework set 6, problem 1. It had this. What's that X there for? I didn't do that. Okay. The problem said to maximize over X and Y, they had to be positive. The utility function of X to the alpha, Y to the minus alpha, such that the budget constraint had to be satisfied. I should have a little dot there. I think I put equals M here. Although you could easily imagine it being less than or equal to M. How would that change it if it was less than or equal to M instead of equals M? You have any thoughts on that?
Wouldn't it not change it?
It wouldn't change the answer for sure. It might change a little bit the way you do it, but it wouldn't change the answer. And the reason is this is a utility function where you want to maximize it by spending all your money. There's no reason not to spend all your money. So whether this says equals or M, or equals or less than or equal to M, you know that it's going to bind. Just a reminder, that's what I was teaching you the last week or two about inequality constraints, is that they either bind or they don't. If they do bind, you can sort of just treat them like an equality constraint. If they don't bind, then you can kind of ignore them, where by ignore them, I mean set the corresponding lambda equal to 0. Still has to hold, the inequality still has to hold, but if it doesn't bind, then because lambda equals 0 in the solution, it kind of doesn't affect the first order conditions. That's what I'm saying. Okay, but in number 1, it happened to be equality. If I show you a problem like this, but then it's an inequality, don't get freaked out. It's pretty much exactly the same thing. You could even argue, if you want, that it's binding, right? If you can give me a reason why it's binding and therefore it's equal, then you can almost start with that. Like, okay, well, we know this one's binding, so let's go from there. All right, let's do this problem. First thing you do is write the Lagrangian, right? Probably could have started with that. It is X to the alpha, Y to the 1 minus alpha, plus lambda M minus P of X, X minus y. Is that right? We want to take the first sort of conditions. Alpha X, alpha minus 1, y, 1 minus alpha, plus lambda M minus P X, X. Oh, what am I doing? I'm just writing the constraint again. I'm sorry, guys. Obviously, that is wrong. What should I have written here? That was a test to see if anyone was paying attention and you were going to stop me.
Is it minus lambda px?
Correct. Equals 0. Should we do y also? Yeah. Thorough. I think here we get 1 minus alpha, X to the alpha, I would say this one does have a lot more, it has more characters, right? Variables and parameters and a bunch of letters and Greek letters all mixed up. So I guess if that's what you mean by harder, then yes, this one is harder. It just has more stuff going on, I would say. That is true.
Don't you have to decrease the y by 1, the exponent?
Oh gosh, thank you very much. I'm just like copying it down. Is that good?
Yes.
Thank you, thank you. And then minus lambda py. I won't make these types of mistakes when I'm grading your exams, I promise. Or when I have it, when I make an answer key for an exam problem that I give. Okay, what I always do in these sorts of situations is to solve for lambda and then eliminate lambda. It's a good strategy here, right? What I would do is, does anyone mind if I use the eraser tool to simplify this? As opposed to writing it out again. I'm gonna do this. This. And erase the equals 0. I'm going to erase this, and I'm going to put a divide both sides by px. Since I need the space, I'll just do 1 over px times that. See, I solved for lambda. I'm going to do it again for the bottom and get 1 over py. That. Agreed? If you're following along and everything, please stop me if you have any questions. I think of today as being a review day. And a review day is not, you have to sit there and just listen to me talk and just hope you understand as much of what I say as possible. This is actually for your benefit, which means certainly anytime you have a question or just want a little bit more explanation, feel free to stop me. It's totally okay to do that. It's encouraged, in fact. So now I'm going to eliminate lambdas and set these two things equal to each other. I will actually do that by writing it here. No more shortcuts here. I'm going to write it out. Dy 1 minus alpha x to the alpha y. I'm also, because I think, who is it that's been saying? Colin is the one who's been saying this one's difficult. I'm going to go slowly for these next few steps. Sorry for those of you who got it easily and you're going to be bored by this. You can like take a break and have some lunch or something. But because it might be difficult for people for whom why would it be difficult? It's because you still don't have enough practice with algebra. I think that's what it is. It's not that you can't do algebra. Of course you can. You're a college student taking an upper level economics course. You can do algebra, but you may not have enough practice doing it so that it's just easy and natural, and you don't make mistakes. Okay, so let's go slowly. And what should I do now? I have this equation, left side, right side. I would like to, my goal is to maybe solve for y. Y equals something in terms of x. That's usually a pretty good goal in these sorts of problems. If you have a constrained optimization problem, you have two choice variables, x, y. You're using the method of Lagrange multipliers. You're probably going to have a multiplier in there, a lambda. I think usually a good step is to first eliminate that lambda from the set of first order conditions, which I did. Then the next thing would be solve for one choice variable in terms of the other. Doesn't matter which one. How about y? Solve for y in terms of x. That's a good next step to do. So what should I do here? I am going to multiply both sides by y to the alpha. And the reason is because I see there's a y to the negative alpha on the right-hand side. I know if I multiply y to the negative alpha times y to the alpha, those will disappear, right? Let me just write that up here. Oops. If I take y to the negative alpha times y to the alpha, that just equals 1. Everyone agree? Okay, so I'm going to multiply both sides by y to the alpha. What do I get? I would like to do the next step too of moving things. No. Well, So I do this, just this one thing. I guess I'll just do this one thing. But I will start writing this at a little more compact. Alpha over px times x to the alpha minus 1. Now I have y to the 1 minus alpha, but I'm multiplying both sides by alpha. So like the question is, what is y to the 1 minus alpha times y to the alpha? The answer is y. Okay. This is, I mean, just using the fact that if you multiply two exponents, exponential terms with the same base, and then when you multiply together, you just add the exponents of the, that's the answer. You add the exponents together. 1 minus alpha plus alpha is 1. That's why it's y. So on this side, I just have a y. On the other side, I have let me simplify this a little bit. 1 minus alpha over py. And the x to the alpha is still there. But the y to the negative alpha goes away. That was the whole, in fact, the whole point of what I did. Still not done because I have an x on the left side and I want that to go away. I want that to go away. So what do I want to do? Multiply both sides by x to the what? What should I do? Multiply both sides by x to the, how about 1 minus alpha? That'll do it. If I multiply both sides by x to the 1 minus alpha, then that x on the left side will go away. And I'll have something on the right, which I can calculate now. What do I get? Alpha over px times y equals 1 minus alpha y. Now I'm going to, on this side, I'm going to have x to the alpha. Oh, right over here. This is my little scratch board for getting things done. X to the alpha times, not x to the alpha minus 1, it's actually x to the 1 minus alpha. Remember, I'm doing the same thing to both sides of the equation. So on the left side, I'm multiplying it by x to the 1 minus alpha. On the right side, I need to multiply by x to the 1 minus alpha. And that is simply x. Because I want to add alpha plus 1 minus alpha, the answer is 1. X to the 1 power is x. We have this. Agreed?
Yeah.
Great. What's my next step? You know what I'm going to be doing here? I'm going to change color. Let's go back and think about what we're going to want to do is plug this stuff back into there, aren't we? We're going to want to find an expression that we could easily plug back into there. How about instead of solving for y, I solve for py times y. And the only reason I would do that is, I mean, it doesn't really matter, just, save a step. Knowing that if I could substitute something for py times y, then I'll just plug it right in there in that what I've circled in red. And you know what, maybe the better thing to circle, the better thing to circle would have been this. Sorry. Now look what I've circled in red. If I could substitute something in there that eliminates y, that's a good thing. How could we do that? Well, there's a py times y in there. How about we just solve for py times y? Using this equation, what will we get? Here's what we'll get. Multiply both sides by py and divide both sides by alpha and multiply both sides by px. That's what I'm doing. Multiply both sides by py, that's why I have a py over here. Oops. Got a py here and a y. I still have a 1 minus alpha on the top. But now I have an alpha on the bottom I divided by. And now I have a px on both, I'm multiplying both sides. So there's one over here, x. Agreed? If I did it all right, this is, I think, the answer. Well, not the answer. This is something that I'm going to use. I'll do it in green. How about this green relationship? I'm going to use it and plug it into there. The reason I'm going to do that is to eliminate y so that I can solve for x. Once I've eliminated y, the only thing left, the only choice variable left, will be x. This will in fact solve for x. This is the way to solve for x, is to eliminate y from this equation. And I can do that now. Any questions? Any questions? Oh, sure.
Initially you said we wanted to solve for y, so
Oh, sure. It doesn't matter. Yeah, Kai, if you want to solve
Yeah.
for y, let's solve for y. If you'd rather solve for y, you can just get rid of this, and it will be a over py in the numerator denominator here. And then once you plug it into that red thing, the py's will cancel out. See how it doesn't matter?
Yeah. Okay.
Yeah, it doesn't matter. Yeah, I mean, and certainly like on your homework, if you did it that way, I'm not going to take off. I'll say, oh, good, yeah, you did it. You also did it the right way, so it doesn't matter.
Yeah. Okay.
What matters is, what do we get after we plug it in? After we plug it into the constraint, I'm going to need some more space. So let me erase the Lagrangian. That's okay. Maybe even this first order condition. That's okay. And these identities that we had. Maybe I don't need this either. Okay, made some more space. But we realize what our goal is to eliminate y in that constraint that I've circled in red, so that what we get is px times x plus py times y. Well, what's py times y? Well, it doesn't matter if we do it the way I was about to or the way that Kai did it. If I take what's written here and multiply it by py, what will I get? The answer is 1 minus alpha over alpha times px times x. All of that equals m. Now I have to solve this for x. Well, luckily, it's linear in x. So I can just see, well, what's the coefficient on the right side? Let me factor out an x. X times what? X times px plus 1 minus alpha over alpha px. I think I could actually simplify that, but for now, let's leave it. Equals m. Can I make some more space by eliminating this stuff? It's kind of like if I had a chalkboard or whiteboard, that's what I would do. I'd write lines, and then once I get to a new line, I would have to maybe eliminate some of the stuff from before. It's okay. Do you see any way to simplify what's on here? Let's call it a, just for fun, let's simplify what's inside the parentheses and say it's what? Px times times what?
Take a px out and then do times 1 plus 1 minus alpha over alpha.
Good, which I think we can also simplify. 1 plus 1 minus alpha over alpha. That's good. This whole thing equals m. What does 1 plus 1 minus alpha over alpha simplify to? 1 is equal to alpha over alpha. So we have alpha plus 1 minus alpha. I believe that whole thing simplifies to just 1 over alpha. Anybody want to see that? Just like 1 becomes alpha over alpha plus 1 minus alpha over alpha. That whole thing comes to 1 over alpha. Okay. That's nice. So actually what we have here is x times px times 1 over alpha equals m. Hey, we're awfully close to solving for x, I would say. I would say that we have our solution for x, and that is x, I'm even going to call it x star here. X star equals m. There's an alpha in the numerator because I'm multiplying both sides by alpha. There's an m in the numerator because it's already in the numerator, and there's a px in the denominator. It actually simplifies to just those three things. After all of that work of moving moving variables around, we get x star equals alpha m over px. Not that surprising though, actually, if you think about it. This question is how much money, sorry, how many units of x should I buy? Well, px is the price of x, right? M divided by px, what is that? That's how many units of x I could buy if I spent all my money on x, right? If m is $1,000 and px is $10, that's the price of x. That means if I spent all my money on x, I could buy 100 units of x. What is this equation saying? Well, if alpha were equal to 1, you'd spend all your money on x. Yeah, that's right. If alpha were equal to 1, x would be the only thing you care about, and you'd spend all your money on it. If alpha were equal to 0, that means you don't care at all about x. You wouldn't spend any of your money on it. That's right. And if alpha is somewhere between 0 and 1, it's sort of saying, what fraction of your money are you going to spend on x? That's what it is. And it turns out to be really smooth. I gave this problem to you knowing that the answer was going to have this really nice, natural, smooth interpretation. Part of that is because this is a Cobb-Douglas function. See, x to the alpha times y to the 1 minus alpha. It's Cobb-Douglas. Very nice properties those functions have. Okay, but we're not done. We should also say what y star is. What is y star? You should use one of these equations, which I got rid of, but I can tell you right now, it's going to be this 1 minus alpha m over py. It's going to be the answer. How do you get that? Plug it back into this red equation that I've circled. Plug it back in. You'd get px times x equals alpha m. Subtract both sides by alpha m. You get 1 minus. You'd get alpha m plus py y equals m. Then you would get py. You would basically get what I have here. The right side would become 1 minus alpha times m. And the right side would be py over y, py times y. And then from there, you would get the answer. Okay, so this is the solution. You might ask, what about how should we prove that it's the solution? Should we check that lambda is positive? Well, actually, this was an equality constraint, so you don't have to check that lambda is positive. But yeah, I didn't ask you to check the second order conditions. I don't think you need to in this problem because it's a utility maximization problem. And this is going to be the solution. You guys have any questions? How I got this? Should I go on to number 2?
Yeah, I get it.
Go to number 2? Great. Let's do number 2. I'm going to delete this. I mean, I think I'm recording this so you can go back and watch it, but I will clear my drawing. Okay. Number 2 is that the Kernel-Blotto problem? I think it is. Should I go check to see what it is exactly? Can we just go right to the Lagrangian? Let's skip out writing out the word max and just go right to the Lagrangian for number 2. It is. I might have to look at it. I'm sorry. I have it here. Here it is. Here it is. X over 100 plus x plus y over 200 plus y plus lambda. And this is an inequality constraint, so it's possible. We could say it's possible that that the constraint doesn't bind, even though you think about it, it's going to bind. I think that's it. That's what I have for the problem, the Lagrangian of problem problem 2, homework set 6. Okay, what should we do here? Well, if you were in class last time, and I did post this video to YouTube, I hope I posted it soon enough that you guys could see it if you looked for it. And that was, you absolutely don't have to do this. If you just attacked this problem as written, you would still get the right answer. You'd still get the right answer. But I just have a suggestion for simplicity to say, let's rewrite this as 1 minus 100 over 100 plus x. Won't that be easier? I want x to only appear once rather than twice, and this is a way to do that. And then this will be 1 minus, oops, that's a 200 over. I'm not using any calculus or anything. This is just algebra. This is just simplifying algebra. What happened there? Plus lambda 200 minus x minus y. Okay. What do I want to do? Take the derivative with respect to x. So we always do. What do we get? Okay, if the 1 goes away, the negative 100 over 100 plus x is, well, the negative 100 you could imagine is still there. The 100 plus x in the denominator, well, that becomes 100 plus x squared, quantity squared. And we have to multiply by -1 because the exponent is -1. That is equivalent to just getting rid of this negative. That's what we get for the partial derivative with respect to x. Oh, don't forget there's also a minus lambda, right? That equals 0, right? That's actually not that complicated. That's the benefit of writing it. It's just simplifying it a little bit before you take the derivative. You can always do that. You can simplify after the derivative, before, whatever's most convenient for you is probably what I recommend. So what are we going to do? We're going to get one for y also. That one's going to be 200 over 200 plus y squared. It's going to be minus lambda equals 0, but right now I'll just write equals lambda and change this one also to equals lambda. Why? Because just like before, the first step is going to be to eliminate lambda. So really natural and wise first thing to do in a situation like this. So forgive me, but I will erase some of these in order to put them together. I want to put them together. 200 over 200 plus y squared. Okay. This is not a solution, but this is a condition that we're going to use to work toward the solution. A little weird. I don't need so many participants to be shown. Okay, well, fine. What should we do here? I like to cross multiply in a situation like this. I'm looking at this and I say, oh man, there's 2 squared things. What if I can put those squared things together? And then if I take the square root of both of those things, then both of the squareds will go away. So that's, in my mind, that's what I'm thinking when I see something like this, like, oh, 2 squared things. Should I multiply them out? No. If you can avoid multiplying them out, that will save you time. So what should we do here? Let's write this as, oops, this 200 plus y squared over 100 plus y squared equals 200 over 100. That's supposed to be a 0 here. Right? You see what I did? I just cross multiplied, meaning that divided both sides by 100 and multiply both sides by 200 plus y quantity squared. And this equals 2. So I'm going to change the 200 over 100 to 2. Now what I'm going to do is take the square root of both sides. And what happens over here? Well, since they're both squared, the squareds just go away. The squareds go away. We get 200 plus y. Oh, I'm not writing well. What? Let me try to write better. 200 plus y over, oops. What happened to, why do I have y on both sides? That should be an x. Sorry, guys. That should have been x the whole time. Okay. 200 plus y over 100 plus x. Agreed. Now what can we say? Well, once again, if you want to, you can sort of look forward to what am I going to want to do? I'm going to want to plug it into the constraint, which is 200 minus x minus y. But there really is no way to simplify that other than just to solve for x or y. That's what we're going to try to do here. Let's multiply both sides by 100 plus x. We get 200 plus y equals the square root of 2 times 100 plus x. Now, if I want to subtract 200 from both sides, I get this. So this is kind of nice. I just solved for y in terms of x. This is usually the next thing you want to do. First, eliminate lambda. If you've done that, then solve for one variable in terms of the other. And then what? Plug it back into the constraint. Here's the constraint. Of course, the constraint is that that equals 0. Here's where the first time today that it might matter that we're talking about an inequality constraint. And what is the method I would like you guys to use when you come across an inequality constraint? I don't know if I would like you to use that. My suggestion is to first just assume that it binds. Meaning you can treat it like an equality constraint and check to see if lambda is equal to 0 or positive. As long as lambda is not negative, that means you were right to assume that it was a binding constraint. In which case, you just proceed. I'm trying to think if there's some possible exception to this. If I'm making an assumption like monotonicity, it is possible that there are some really bizarre situations where this method won't work. But I've told you that I won't give you problems like that in this class. If you're going on to grad school and you want a more comprehensive method for solving problems like this, there is another set of conditions called the Kuhn-Tucker conditions, named after two economists, Kuhn and Tucker. And those are a little more comprehensive about when we can say for sure that this is a solution or not. But I don't think we need those for this class. Just use the method that I described. Assume that it's binding. Check to see if lambda is non-negative. If it is negative, then go back and change the assumption that it was binding and say, okay, well, let's say lambda equals 0, and then solve the problem that way. Okay. What do we do? So we're going to plug that into the red and get what? I think I need some more space for myself, if you don't mind. And get rid of this rewriting of the Lagrangian. Maybe even get rid of this. Probably even this. Do I need any of this? I'll save what I have on the bottom, what I've concluded, but not anything else. Okay. So I concluded what I've written there on the bottom from the first order conditions. Now we need to plug it back into the constraint. What do we get? we gonna get 200 minus x minus y. Well, instead of y, we'll write this whole thing. And that is the square root of 2, 100 plus x minus 200 equals 0. Is this good? I've plugged in for y what I've solved for below. I think I did it right. Nobody sees any issues with what I've done so far? Does it look good? What do I see? Well, I see, wait a second, the 200s don't cancel out, do they?
No, they don't.
Is this right that this is yeah, I mean, hopefully I didn't make a mistake in my formula there at the bottom, y equals. Is this what you guys got? Did anybody get like this far when they did their homework?
I didn't do like how you changed it like initially to the 100 over 100 plus x. Like I didn't think of that.
Okay.
So I didn't get to this, but I also I was struggling with this problem, so I'm not.
Yeah. Well, so let's say you didn't use that little shortcut. You should still get something equivalent to this once you've eliminated lambda and solved for y in terms of x. I guess what I'm saying is, unless you made a mistake in the calculus or the algebra, you would still get something that looks very similar to this. And I guess, go ahead.
I think like the square root 2, like getting rid of the squares or something, I didn't do it correctly.
Yeah, so I guess what would I predict would happen if you didn't see the shortcut of just leaving them squared and then taking the square root of them, then you would get these maybe relatively complicated algebraic expressions that have x's and y's in them together. And that could be very difficult to solve. If you just treated y as the variable and x as a constant just for that sort of equation, though, you should still be able to get an answer, but it would be very complicated. It would be like 2 pages of algebra rather than just 4 lines of algebra. So I mean, I really yeah, sorry, I tried to give you this hint sort of at the end of last class that leaving it squared will help. It will, and it should.
I think I was a little confused because my lambdas canceled out initially because I did like the FOC1 and FOC2.
Yeah.
Yeah. So I don't know. My FOC1 was 100 over x plus 100 squared minus lambda equals 0. And then
say that again. 100.
100 over x plus 100 quantity squared.
Okay.
Minus lambda equals 0.
Okay.
And then my FOC2 was like the same thing, but it was 200 over y plus 200 quantity squared.
That sounds right.
Minus lambda. But then because there was lambda in both, I just set them both equal to each other. And then
that's right. That's what you're supposed to do.
Okay. I'm wondering where I went wrong because my x and y's have like decimals for like the actual value.
Well, maybe because of the square root. Did you multiply out the square root of 2? Did you calculate the square root of 2? What you just told me is exactly right. Those are the first order conditions, and you should set them equal to each other because they're both equal to lambda. You should get exactly that, what I have on the screen here. And from that, you get this.
Why does it look so different to me? Because yeah, my y, like it got down to be, it was y squared equals 2x squared minus 20,000. And then it went into y equals.
You got y squared equals 2x
squared minus 20,000, which was just
K. I don't think that's the same. Could it be? Maybe it is. I do
Is
see
my-
like
is my
the
y-
relationship between y squared and x squared is correct because, you know, if you squared both sides here, you would have a radical 2x squared, but there would also be this other term. You'd have some x's in there, which you don't have.
Is it wrong to cross multiply from the previous step? Because I cross multiplied and did like 100 times 200 plus y squared equals 200 times x plus 100 squared. And then I
Yeah,
saw,
that's right. That's correct. You should still get this answer.
okay, maybe when you check my work, it might show up. Yeah, I'm just trying to
Yeah.
figure out. Yeah,
Maybe your answer is totally right, in which case we don't even need to worry about it.
Okay.
But let's see. I think what I have written here on the screen is correct. People seem to be confirming it. So let's simplify it and let's solve for x. That's our goal right now, is to solve for x. We have a 200 here and also a positive 200 here, which means that will become 400. 400. We have a negative x next, but we're also going to have a minus the square root of 2x in there. You see that? Negative x minus the square root of 2x. So that is going to be, I'll say plus, I guess I'll say -1 minus the square root of 2x. And then the only other thing I have here is a minus the square root of 2 times 100. Or I'll say 100 radical 2 equals 0. And that's right. And now I want to put everything that's not x. I'll leave everything that's not x on the left and move the x's to the right. I get f 400 minus 100 radical 2 equals, now there's an x on this side. I have to reverse the sign. It becomes 1 plus radical 2. And if I divide both sides by 1 plus radical 2, I should have an answer for x. Did anybody get this as their answer for x? I need a calculator here to even just say what this is.
I did. I got a 107.11.
You know what? That sounds right. Who said that? Jonathan?
Yeah.
I think that's right. So, I mean, should we calculate it here just in case? 400 minus 100 times the square root of 2. Oh, this is, no, I think that's right. I think that's right. No, not MATLAB. What am I doing? Okay.
Yeah, I just calculated it and it is 107.
107. So let's say it's approximately, and we'll call it x star. Oh, by the way, though, we should check to see what lambda is. But right now, let's just assume that it's correct and call it x star is approximately 107. What if we want to find y? Well, we can find y by this formula right here on the bottom. Now, instead of 100 plus x, we plug in 107 and we get, square root of 2 times, plug x into 107 into there. And does anybody know what we get for y star? Oh, by the way, I know what we get. It's 93 because x plus y should equal 200. So y star should be equal to 93 in this case. So we have a potential solution for x and y. And we assumed that the constraint was binding. Technically, if we want to go back and say, were we correct in that assumption? We should look and see, well, what's lambda in this case? And darn it, I erased the first order conditions with lambda in them. But I think I could remember them pretty quickly. It was something like 100 over 100 plus x squared equals lambda, right? We just want to make sure that's not negative. I can look at it and tell immediately it's not negative, right? No matter what x is, that's not going to be negative. It's a positive number over something squared. It's definitely definitely positive. So we're good. And these are indeed the solutions. I might make them green. You guys have some questions about how we got here? It's the same method as the previous problem. Write a Lagrangian. Write out the first order conditions. Solve for lambda and eliminate lambda. Then you have the two choice variables. Solve for one choice variable in terms of the other, and then eliminate that in the constraint. Solve for the choice variable, then solve back for the other one. Solve for the exact values of the two choice variables, and that's the solution. Because this was an inequality constraint, you might want to go to the next step and see, was lambda really positive or 0? And the answer is yes, it was. Which means the constraint's binding, which means this is the solution. You guys have questions?
Yeah, Professor.
Sure.
So when we're answering the questions, like one is just finding x star, y star, and lambda good enough? Would you make the assumption that because lambda is greater than 0, x star and y star are the solutions? Or would you like a few sentences describing that idea?
I don't think a few sentences are necessary, isn't it? Just one? How about just one?
Just one. But yeah,
And they can be phrases even. It might be nice to have some acknowledgement that in this problem, there was an inequality. And the method you use to solve it is assuming that the equality is binding. Now, what if that was a bad assumption? Then your solution might not be correct. So it's nice to just go back and say, well, this assumption that we made that the constraint is binding turned out to be correct. Therefore, our solution is valid. I mean, you don't have to write. I think it would be nice to just write what I just said, approximate that in your answer, so that I know that you know how you got what you did. Okay.
yeah, sounds good.
Cool. Do you guys want to see 3? Or anybody else have any questions about number 2? Or does anybody want to see 3? We got some time. We could go back and review any of the other problems, any of the other topics from this year, this semester, like total derivatives or the implicit function theorem corollary or unconstrained optimization. For those, remember, I might ask you about second order conditions. I think I pretty much said the, oh wait, and constrained optimization. I might ask you a second order condition if it's an equality constraint, in which case you can use something called the bordered Hessian. This is like the normal Hessian, but it's bordered with the partial derivatives of the constraint function on the row and an extra row and an extra column. Of course, and there's one, the top left of the bordered Hessian is 0, but you know, I want to just draw what I'm saying. Here are all drawings. Remember, this is just a review that for let's try to review this for unconstrained. Oops, I want it to be black. Unconstrained. The second order conditions are what? Determinant of the Hessian should be positive, negative. What should it be? Answer is positive, right? And fxx should be negative or max, and positive or min. Isn't that right? For the constrained with equality, what what is the second order conditions there for the optimization problems? You guys remember? We're now talking about the bordered Hessian, which can be written as H bar often, if you like. You still want to look at the determinant of the bordered Hessian. And we say, if it's positive, then what? Is it a max or a min?
It's a constrained max.
Very good. It's like backwards of the one that's right above it. And if it's negative, it's a min. Yeah. And then for inequality constraints, the second order conditions are, I never taught you them. Sorry. I never taught you those, so I'm not going to ask you about them on an exam.
I have a question about the bordered Hessian.
Sure.
So a couple classes ago, we talked about like the bordered Hessian matrix and how in the second row, instead of f of x of x, it's L of x of x. Does that make sense?
Yes, and I apologize for that. I hope maybe you were there for my apology, but yeah, I initially put F in the PowerPoint slides. I did change it, and the PowerPoint slides, I think, now have an L instead of an F.
Okay, so you just find the second derivative of the Lagrange equation.
Correct.
Okay.
With
Okay.
respect to, XX, XY, YX, YY.
Gotcha.
Yeah,
Okay.
yeah, that is correct.
The entire equation, not just the Lagrange part of it.
Yes, and the only difference is, well, maybe there's a G in there somewhere, right?
Yeah.
By that, I mean the constraint function. If it's linear, it goes away. It doesn't matter. Wouldn't you agree?
Yeah, yeah.
So the times when it might matter is when you have a non-linear constraint function. And, of course, I should have told you that from the get-go, that in case there's some part of the G that should be included, it should also be included in the bordered Hessian.
Okay.
Yeah, let me just write that out for you right now. I'm going to clear these drawings. The bordered Hessian is equal to 0 gx gy, also gyx gy, but here is L x x, where L is the Lagrangian. L x y, L y x, which of course is always equal to L x y, L y y. Yeah. And hopefully you know how to do determinants. If you want to, it's a take-home exam. If you want to do a determinant, you can do it multiple ways. You could do it by hand. You could use a calculator, an online determinant calculator. I'm okay with you using that. Right. If you're not showing your work though, let's say you're doing a problem and you just like jump to the answer. I would be careful about that, because if I think there's no way you could have gotten to that answer without some steps of work that are relevant, and you ended up using a computer to do it, I would still like you to say that you used the computer, right? Don't make this confusing for me. Like, how did you get that? Either write your steps out so I could see, or tell me what sort of computer program you used to get the answer. Please, I would like that as a courtesy to me. Please do that. Thank you. You guys want to do problem 3 from homework set 6, or what?
If you could maybe just like talk about it for a second. I know you emailed me and we went back and forth for a second. I just don't really get, like, I know that x had to be less or equal to 3. So you told me to do the lambda 1 and lambda 2.
Yep.
And I don't know, I was just kind of like wondering where they cancel out, I guess.
Yeah. I think I can do it pretty quick, Colin, and you'll see. what I mean. Plus, why did that happen? Plus lambda 1. So there's a subscript on lambda now, and that's 40 minus 8x minus 5y. And then there's a lambda 2 for the second constraint, and that one is just simply 3 minus x. So these problems I find to be interesting because there's more than one constraint, and now it's like, it's not a trivial problem. Which constraints bind and which ones don't? Do they both bind? You know, it could be one but not two, it could be two but not one, or it could be both. It's really unlikely that neither one binds, right? Just like before when we were talking about utility maximizing, you know, some constraint has to bind. Otherwise, you know, because more is better because of monotonicity of the objective function. Okay.
So anytime we have multiple constraints, we should do more than one lambda.
Yes.
Okay.
I think you missed that lecture. We did that. We did this.
Okay.
It was more
Okay.
than one
Yeah, that's why I was confused. Yeah.
Yeah. More than one lambda. There should be one. They're called multipliers. There should be one multiplier for each constraint. If
Okay.
for some reason I went crazy and gave you 3 constraints,
Then
I
we
could do that. I could give you a problem with, I'm probably only going to give you 2 choice variables, but maybe I give you a problem with 3 constraints. And you're like, what do I do? Make a lambda for each constraint, call it lambda 1, lambda 2, lambda 3. Start the problem out as if all 3 constraints bind, and you'll probably get to this point where, wait a second, you know, if we make that assumption, then this lambda here would have to be negative, and that's not possible. So, you know, you get to some kind of contradiction, and then you would say, well, probably it's this constraint that is not binding. Let's let that lambda equal 0 and continue on with our assumption that the other 2 bind, and you get a solution. And if in that solution you find, wait a second, we still have a lambda that's negative, then take that one and make it 0 and do it again. And then now you have fewer first order conditions to work with, because every time you make lambda 0, you're sort of reducing the number of variables in your first order conditions.
Okay. And we should always solve for lambda first, right? And then get into x and y? Or I guess-
Oh, no. Okay, so when you say solve for lambda, you mean in terms of the other variables?
I guess like for me now I understand like how to get the first order conditions, and that's pretty easy. I just never really know like what to solve for first. And I had been doing like solving for y or x or whatever, like seems easy.
Yeah. So to actually solve for, I recommend solve for x and y first. But the way you solve for x and y is to write lambda in terms of the other variables and then eliminate lambda. So you do work with lambda first because it's the easiest thing to eliminate. I'm running out of time here. Let's actually look at this problem. I think I can show you pretty quickly how to do it. Lx becomes what, 2xy minus 8 lambda 1 minus lambda 2. That equals 0. The next one comes x squared minus 5 lambda 1 equals 0. This one becomes just the first order constraint, the constraint. Do I really need to write it out? Yeah, I'll write it out. And lambda 2 is 3 minus x equals 0. See this? I have a first order constraint for each variable, including the choice variables and the Lagrange multipliers. I have one for each. Now I'm going to just be naive. Maybe it's naive, maybe it's not. Maybe it's really clever to say, let's solve this system of equations, assuming that they all bind, meaning that they all hold with, all these first order conditions are true. That's what I mean. Okay, well, from the very bottom one, we get x equals 3. Interesting. If I plug that 3 into the next one above it, I get 40 minus 8 times 3, which is 40 minus 24, which is 16, equals 5y. So y is going to be equal to 16/5. Did you guys get this? Y equals 16/5. Am I doing this right?
That's
Okay.
what I got.
Great. And then, well, how about from this one? This one will tell us something about lambda 1. This one will tell us something about lambda 1. X squared minus 5 lambda 1 equals 0. So lambda 1 equals x squared over 5, which is 9/5, which is positive. Really, all we care about is it positive? Yes, it is. Okay, now from this one, we're going to have 2 times x times y. That's 2 times 3 is 6. 6 times y is 6 times 16, which is 96 over 5. We got to write that here. It might actually matter. 96 over 5 minus 8 times lambda 1. All of this matters. All of this matters what lambda 1 is and that there's an 8 there. And 8 times lambda 1 is actually 8 times 9 over 5, which is 72 over 5. 72 over 5. And that equals lambda 2. It's pretty close, but actually lambda 2 is positive. And the fact that lambda 2 is positive tells us that we were correct to assume that both of our constraints bind and that this is a valid solution. We don't have to go any further. I didn't give you a really long, lengthy problem here. If you had found that, this is 96 and 72, those numbers are close. If it had been just a little bit bigger, then you would have found that, okay, lambda 2 is negative. Oh, geez, that must mean we ignore lambda 2. We set lambda 2 equal to 0, and we solve the problem that way. And that would give you the answer that you got, Colin. I saw your homework, which you emailed me. You got an answer where like x was 10/3 or something like that. That would have been the answer if this other constraint didn't bind, the 3 minus x equals 0. If it was instead like 4 minus x equals 0, something like that, then because 10/3 is less than 4, you would have found that, oh, in this case, that constraint is binding and the one that you found is correct. But unfortunately, the one you found is not correct because this constraint, the 3 minus x equals 0 one, is binding because these lambdas are positive. That's a lot of words. But what I'd like you to understand is that this, I could even put stars here. This is a solution. And the reason it's the solution, the reason we know it's a solution is because we found an x, a y, a lambda 1, a lambda 2 that are both positive, that solve the system of first order conditions from this Lagrangian. So that's a solution. You guys you have any questions about that?
No, you made it way easier than what I did.
Yeah. No, of course this didn't have to be the end, right? If one of the lambdas had been negative, then you're like, oh darn, now I got to, you have to do another step. But it just turned out that this is the final step of the process. What else can I help you guys with? I don't know if I'm gonna see much of you again. This is kind of like pretty much the end of the road of our class. I do want to have a final exam that I will make available to you. How about on Friday? It'll be due on Tuesday. At the end of our normal, exam period time. You have at least that exam period to work on it because I know that time is made available to you because you're enrolled in this class. But I'm going to stop recording.